To understand a massive population, we rarely have the luxury of measuring every single unit. Instead, we pull a tiny fraction of that reality and attempt to map the whole using only these data fragments. The objective is to determine the true, unknown average of an entire group, the population mean, represented by the Greek letter mu. To find it, we extract a small subset and calculate its average, the sample mean, or x bar. In statistics, this single calculated number is called a point estimate. It represents our calculated estimate of the truth, based entirely on the limited data available. A point estimate alone projects false precision. Being a single coordinate, it contains no measure of its potential error. To solve this, we replace the point with a confidence interval. We expand outward in both directions by a specific distance called the margin of error. We achieve statistical rigor by mathematically defining the exact boundaries of our own uncertainty. Generating a valid confidence interval is not an automatic process. The underlying data environment must satisfy two non-negotiable system requirements. First, the data must be collected via a simple random sample. Every item in the population must have an equal chance of selection, eliminating selection bias from the process. Second, the sample size, denoted as n, must be strictly greater than 30. If the sample is smaller, the population itself must already be naturally normally distributed. Violating either of these conditions corrupts the geometry of the probability curves we rely on. If these assumptions fail, the final calculated interval is mathematically meaningless. Robust statistics requires both unbiased data collection in the field and strict adherence to probability mechanics on paper. When calculating the margin of error, we encounter a practical obstacle. Researchers almost never know the true standard deviation of the entire population. To move the math forward, statisticians use the standard deviation of the sample itself, represented by S, as a stand-in proxy. This introduces a secondary layer of uncertainty. In small samples, the standard deviation fluctuates from one test to the next, creating a level of variance that standard normal distributions cannot properly handle. The student t-distribution was engineered as the mathematical correction for this specific problem. This chart shows the standard normal distribution in green alongside the t-distribution curves in blue and purple. The t-distribution compensates for small sample variance by using a lower peak and wider tails, pushing probability to the extreme edges. The t-distribution is dynamic. As your sample size increases and the sample standard deviation becomes more reliable, the curve physically tightens until it aligns perfectly with the standard normal curve. The t-distribution functions as a dynamic geometric correction for missing population data. With the t-distribution established, we can calculate the exact margin of error E to define our boundaries. The formula multiplies our sample's standard error by a critical value, denoted as t alpha over 2, dictating the interval's width. To find this t-value, we calculate degrees of freedom, our sample size minus 1. This selects the exact curve for our dataset. Next, we set our confidence level, such as 95%. The remaining 5%, the mathematical doubt, is represented by alpha. This diagram shows a t-distribution curve for 5 degrees of freedom. The 5% alpha is split equally into the two tails, leaving an area of 0.025 on each side. The boundary separating that tail gives us our critical value, 2.571. Choosing a confidence level is a deliberate trade-off between the precision of your interval and the probability of being correct. We apply this to a quality control test, verifying the accuracy of a factory production line using a sample of exactly 6 peanut butter cups. The package label claims a target mean weight of 8.953 grams. Our sample of 6 yields a sample mean of 8.8057 grams. Because our sample size of 6 is below the threshold of 30, we must verify that the cup weights are normally distributed before we can proceed with the calculation. This is a normal quantile plot of our data. Because the sample points follow a straight line pattern, we can confirm the data appears to be from a normally distributed population. With n equals 6, we have 5 degrees of freedom. For a 95% confidence level, our t-distribution table yields a critical value of exactly 2.571. We calculate margin of error by multiplying the critical value by our standard deviation of 0.2054, divided by the square root of 6, yielding 0.215589. Applying this margin to our sample mean defines the final boundaries, 8.5901 grams to 9.0213 grams. This means that if we ran this 6-candy sample infinitely, 95% of the generated intervals would successfully capture the true factory-wide average. The factory's target of 8.953 grams sits inside our calculated boundaries. Because the target falls within the interval, the manufacturing process is statistically verified. While we can analyze existing data, we can also use these mechanics to architect an experiment from scratch. In experimental design, our objective is calculating the exact minimum sample size, n, required to achieve a predetermined margin of error. We algebraically rearrange our formula, isolating n on the left side. This calculation uses a z-score, the target margin of error, and the population standard deviation. This formula contains a circular requirement. It demands the population standard deviation, sigma, before any sample data is collected. High-level design requires researchers to estimate this missing information using preliminary tests or historical data before the study can launch. There are 3 standard workarounds to estimate the missing sigma: the range rule of thumb, a small pilot study, or leveraging historical prior results. Suppose we want to estimate the mean IQ score of statistics students, demanding a 3-point margin of error at a 95% confidence level. Based on prior results, we estimate sigma to be 15. Our target margin of error is 3, and our 95% confidence z-score is 1.96. We populate the formula with these specific inputs, resolving to a raw mathematical output of 96.04. In sample size design, you must always round up to the next whole number to maintain your target margin of error. 96.04 becomes exactly 97. By engineering an exact sample size of 97, we establish the specific mathematical conditions required to meet our target level of confidence.